So let's get the show on the road here. So we do have the next exam coming up, and as I discussed, we'll be taking an exam, and will be distributed after the problem session next Friday. Okay? So this Friday we'll have just a discussion section. I'm posting all the solutions. There's only one more solution to post, problem set 9. And so come with questions. All right, and we'll discuss that. If you're not, I will put it on the web immediately after this, so if you're not there at the problem session, you can download it or email it to you, to everybody, probably is what I'll do. Okay. And as I said, we'll discuss a little bit more the rules of the game as time approaches a little bit. Okay. All right. So last time we were talking about an important sort of last ingredient of the formula. Maybe there's one more, you might say, sort of postulate of quantum mechanics that we didn't really discuss at the beginning. It's how do you deal with composite systems? And what that means, classically, we talk about the notion of a degree of freedom. Okay? So in classical mechanics, to each degree of freedom, we assign a set of a coordinate and a conjugate momentum, right? And if I have multiple degrees of freedom, for example, I have a particle that's moving in 2 dimensions, or I have 2 particles moving on a line. Those are 2 examples of systems with 2 degrees of freedom, okay? And we assign some canonical coordinates to each degree of freedom. I'm calling them generically A and B. And in classical mechanics, what we said is that the joint phase space for the system is given by the, formally what we call the Cartesian product, okay? So the coordinates on phase space are these, okay? And that's what we call the Cartesian product. Now, as I mentioned, the division into the degrees of freedom is not unique, necessarily. For example, as I mentioned last time, if I talk about a particle moving in a plane, I could define as my, I could have one degree of freedom be, say, motion along the x-axis, and the other one be motion along the y-axis, and then there's a conjugate px and py. And that's one way to define the degrees of freedom. Or alternatively, I might choose to have xa be the radial, let me call it rho, and the other conjugate, I mean xb, be phi, right? And then there's a conjugate p phi and p rho. So the division into degrees of freedom is not unique, right? And similarly, two particles on a line, I can talk about the coordinate of each particle. I can talk about their relative coordinate and their center of mass, okay? And we'll come back to that. It's going to be important. Okay, so that's classical physics. In quantum physics, what we said was that if I have different degrees of freedom, what is true is that observables associated with those different degrees of freedom commute. Okay? And that means we can define sort of separate Hilbert spaces for degree of freedom 1, or A, and degree of freedom B, with observables that act on each of those Hilbert spaces. And then the joint Hilbert space that describes states of the system that describe both degrees of freedom is given by the tensor product. Okay? And the tensor product is such that we can define joint states of the system that are product states. And we have this tensor product in between them. And what that physically means, because of course the state, in this case I'm talking about pure states, are uncorrelated. That is to say, if I have a product state, the joint probability distribution for degree of freedom A and B is a probability for A times a probability of B. Right? And that means that there's no correlations between A and B, because the probability for both things to happen is just the product of one times the product of the other. Does that make sense to everybody? Why uncorrelated probabilities are products?
Because they're independent of each other.
But why, if that's true, why is it a product? I mean, that's sort of a tautology.
Is it probability theory?
Yeah, so what aspect of probability? I mean, what are we saying when we say
It's
that?
like the cross terms when you do the variance. Like you get just the square, but then you also get the cross term of the covariance. If it's 0, then it's easy.
Sure.
Probability theory.
That's one way of looking at it.
Is this like what we were talking the other day? It's like if I want to look at the probability of flipping two heads,
Yeah.
it's the chance of flipping one head times the chance of flipping the other head?
Yeah,
No?
that's exactly what
Okay, okay.
But so why, if you wanted to calculate the joint probabilities of two heads, why did you just multiply them? Because it seems intuitive to do that, right? Yeah.
But that's like, so if you're doing tests, you want to use just the normal average. But if
Right.
you're doing something like stocks, if you want to take an average, you use the other kind of average, like the geometric average,
Geometric
because
average.
they depend on each other.
Right.
Okay.
The way I look at it is the following. If something's uncorrelated, what it means, the probability of flipping this first coin has nothing to do with what happens to the second coin. So what that would mean is that the marginal probability distribution, which is the probability for A to happen, I can write without knowing anything about B. That is to say, if I want to know what the probability, Zeke, you can have one coin, I'll have one, I flip mine, I can calculate mine independently of yours. And what that says, we know from probability theory, if I have a joint probability for two things A and B, then the marginal probability distribution on A is given by the sum of all possible V values, whatever they are. That's the marginal distribution. Now, if this is equal to a product state of probabilities, well, then it's obvious. This is just the probability of A. It doesn't depend on B. It's just given by that. So that's a key idea from logic. Two things that are uncorrelated, for this and that to happen, is just the product of their happenings. There's no correlation between them. And in quantum mechanics, a state like that we call separable. Okay? And in this case, what it says, the probability of outcomes of observables that act on degree of freedom 1, whatever that degree of freedom is, are not in any way correlated with the outcomes. They're independent random variables. Okay? If the probability distribution is of that form. Let me look at it this way as well, just as if we look at this in wave function land. So suppose that this was two particles moving on a line, okay? So the wave function for this thing is given by this, where these are the position eigenvectors of particle A and particle B, okay? if the state was a product state like this is the wave function, right? The wave function in this case is just the product of wave function A and wave function B. And that means the joint probability distribution factorizes. I'll call it the probability A is a function of random variables and probability distribution B, which is the square of each of these guys. Okay? Yeah.
What if you wanted to say keep track of a particle's position and like spin, if it was spin 1/2 or...
Sure, that's fine too. So for every degree of freedom, if I have, you know, I can have as many degrees of freedom as I like. And then I'd have a tensor product. And we're going to talk about this more. We're going to get back to spin. We haven't forgotten it. We just put it on hiatus. So every degree of freedom is in a tensor product. Okay. So for example, if I wanted to say I have one particle, I want to keep track of its position and its spin, then the joint Hilbert space of the system is L2 if it's moving, say, on a line, tensor, two-dimensional complex numbers. That is the Hilbert space associated with particle having a certain position and a certain spin. That's how we would formally write it. And we'll talk about that. They're called spinners. Yeah?
So the parts where we have, you know, psi AB is equal to psi of...
If that's true, yeah. If it's a product state, yeah.
Oh, if it's product. Okay, so that's not spanning a new space.
It is not.
That's
That's
one member of that new space.
Correct. Correct. Indeed. And in fact, this is the definition of a tensor product space. A tensor product space is the linear span of all product states. And there are states in the tensor product space which are not product states. Okay, for example, I mean, I can write one down in terms of wave functions. Let's say, just as an example, let's say I have two particles in a harmonic well. It doesn't have to be an harmonic well, because I can use the harmonic outside of the wave functions that I like. I'll call them particle 1 and particle 2. The joint wave function might be this. Alpha U0 x1 U1 x2 plus beta U0 or U1 x1 U0 x2. What is this? Well, this is the particle where one of them is in the ground state and the other is in the excited state. But I don't know which one it is. So there's some probability amplitude alpha that particle 1 is in the ground state and particle 2 is in the first excited state. And there's some probability amplitude here that particle 1 is in the first excited state and particle 2 is in the ground state. This is not a product state. There's no way, there is no way to write this as some psi x1, psi x2, or phi x2. This is not a product state. But it is in the tensor product space because it is spanned by product states. In the same way that I could say, you know, a particle or a vector in three-dimensional space is the span of vectors along x, y, and z. But not every vector is along x, y, or z. It's the span. Okay? This kind of state is not a product state. It's not separable. It has another special name called an entangled state. Now, everyone loves to talk about entanglement. It sounds like the coolest thing since puffweed. I don't know why puffweed is cool, but that's what people say. We'll talk more about that to end our semester. Okay. Okay. So, right, continuing on. So, formally speaking, as I said, the tensor product space is the span of all product states. And that is the space that describes the composite Hilbert space for multiple degrees of freedom. Okay? We can always write a basis for the tensor product space as looking at the individual bases for, say, in this case, if this were just 2 degrees of freedom, if I have a basis for Hilbert space A, which has some vectors, and a basis for Hilbert space B, which has some vectors, then a basis for the tensor product space, there exists always a product basis. Again, not every basis need be a product basis, but I can always find a product basis by this construction. Okay? Question: what if the dimension of Hilbert space A is D sub A, and the dimension of Hilbert space B is D sub B, what is the dimension of the joint Hilbert space? D sub A times D sub B. Okay? So the dimension of the joint Hilbert space is just in the product of the dimensions. Right? That's a big deal. Because that means the dimension is growing if I have multiple degrees of freedom exponentially. If I have n degrees of freedom, and each one of those degrees of freedom was associated with a Hilbert space of dimension d, what is the joint dimension of n such things? D to the n. Okay?
Well, it doesn't work if you be one dimension.
What do you mean?
If the dimensions of all of the space states are just one, you gotta just end it with one dimension left over.
It's true, but I think you have to be careful about what you're thinking about here. This is the dimension of Hilbert space. It's not the dimension of physical space along which the particle is moving. If a particle is moving along a line, what is the dimension of Hilbert space that describes all states of motion of the particle?
Is it continuous?
It's infinite. It's infinity, okay? So if you deal with wave functions, you never see this exponentiation of the dimension because it started infinity and the dimension is, oh, it's just infinite. It keeps infinity times infinity times infinity. It's only when you deal with finite dimensional Hilbert spaces that you ever see the exponentiation of the dimension of Hilbert space. Okay? Right, cool. All right, continuing then. So another piece of the formalism we talked about is, of course, we talked about the tensor product of observables or operators. So I can define, if I have an observable, if I said, oh, this observable OA acts on Hilbert space A, maps vectors in this to vectors in that, and we have some other observable that acts on Hilbert space B, then I can define an observable that acts on the composite Hilbert space, map vectors on vectors, as the following, that this acting on a product state is equal to the tensor product of the individual actions. That's by definition. Now, what would you do if this tensor product acted on some general state, and you don't know whether maybe it's not a product state? Well, I can always decompose it in a basis of product states. Okay? So I can insert in here a resolution of the identity. Now, the resolution of the identity is, I'm going to write this, as I said, we have lots of different notations, and sometimes when I write something like this, this is a shorthand for EI Fj outer product with EI tensor Fj. Okay. Or I could think about this as the operator, the projector A tensor that. That's also equivalent. Okay, because this is an operator that acts on Hilbert space A, and this is an operator that acts on Hilbert space B. That's perfectly, they're all the same, they're just written sort of different ways. So this would equal OA tensor OB acting on, I'll call it alpha ij EI tensor Fj, where alpha ij is a probability amplitude associated with that projection. Okay? And then I know how to act this. It's a linear operator, so it comes inside the sum. This guy acts on this basis vector, and this guy acts on this basis vector. A, sorry, thank you. All right. Very good. Now, I want to talk about eigenvectors. Operators. Suppose I had a particular operator on a joint space which was of the following form. It was some operator A, and it did nothing to B. Or it's kind of sum like this. Okay. So A acts on Hilbert space A, and B acts on Hilbert space B. It's a sum of two operators that act on this. Okay? What is an example of an eigenvector of this operator?
An eigenvector of A tensor eigenvector.
Exactly. So if there are, let's suppose A has eigenvectors little a, and B has eigenvectors little ket b, with no code of that, then AB, which is A tensor B, is written, right, is an eigenvector with eigenvalue A plus B. Okay, so this gets confusing, and this is sometimes, let me come back to that and use a certain language here that often confuses, so I'll come back to it. All right, so this tells us something about, if we're looking, in particular if we're looking at, let's go back to the time-independent Schrodinger equation. Okay. So we seek the eigenvectors of the Hamiltonian. Okay. So now there are a special class of cases where the Hamiltonian is of this form. Okay? So suppose we take this, H is the Hamiltonian for multiple degrees of freedom. Okay? Many particles, many spatial dimensions, as much as we like. Okay? So H acts on our composite Hilbert space. For the moment, let's just focus on 2 degrees of freedom. Generalize, it doesn't matter. Okay? Okay? If, so let's say e.g. 2. So if the Hamiltonian is of the form, a Hamiltonian that acts on degree of freedom A, tensor 1 on D, plus does nothing to A, then we say the Hamiltonian is separable. Now it's a little bit confusing because I said that with respect to states, a separable state was a product of a state on A and a state on B. Okay? But in Hamiltonian land or in operator land, this is a different notion of the term separable. Because this is not Hamiltonian A times Hamiltonian B. It's the identity on the other one, right? It's got this sum structure. But those words are used. All right? If the Hamiltonian is separable, that means that its eigenstates are product states from the reason we just said. Okay? So that's why it's called separable. Because you can separate the eigenvector as the product of eigenvector for Hamiltonian A and the Hamiltonian for right? So that we can write energy EA, EB as some, these are the eigenvectors. And the eigenvalues are just the sum of the eigenvalues associated with the 2 degrees of freedom. Now, if we have a separable Hamiltonian, if the Hamiltonian can be separated as a Hamiltonian acting on degree of freedom A and a Hamiltonian acting on degree of freedom B, then what about the unitary evolution, the time evolution of the system? So let's look at that. Let's say we have the time evolution operator. Let me call this HAB. It's the Hamiltonian that acts. This is not the Hilbert space, it's the Hamiltonian. It's got the hat on it, it's not the scripty H, it's the... So now I got my time evolution operator. Let's just say it's a time-independent Hamiltonian, and generally speaking, we know that this is true, right? But let's suppose H is separable. Okay. Then I can write this as a Hamiltonian acting on degree of freedom A, and I'm just going to write it out in its full pedantic glory. times t plus okay. So what can you tell me about that?
You can immediately separate.
Exactly. We can write that as the product of the exponentials, because this commutes with this. Obviously it does, and as I emphasized, the whole point is that observables associated with different degrees of freedom commute. And because they commute, that means I can write this as a Hamiltonian, and I'll leave out the identity part. And that product now is of this form. Okay? So this is the unitary operator acting on Hilbert space A, generated by Hamiltonian HA. And this is the unitary evolution UB, generated by Hamiltonian UB. And the joint unitary is the product of the unitaries. So this is where it gets confused. The Hamiltonian is a sum, but the unitary is a product. And we call this a separable unitary. Okay? Why is this interesting? Well, if this is true, then what it says is that if I start with a product state, so if at time t equals 0, the joint state of the system is a product state, which means there's no correlation between them. But the A on the opposite, I need to say it's K in space A and K in space B. Then what can we say about the state at a later time? Well, we apply that. Yeah. And then what? So I get UA acting on psi A, tensor with UB, tensor acting on phi B. All right? This is just this, tensor this. It's always a product state. Okay? So if my Hamiltonian is separable, then if I start in a product state, for all times I stay in a product state. Which means if there was no correlation between degree of freedom A and degree of freedom B at the initial time, then there never are correlations generated between them. Which is to say that when the Hamiltonian is of this form, the degrees of freedom don't interact. So physically, to say that the system is separable between A and B is to say that the two degrees of freedom don't talk to one another. There's no interactions, there's no correlations between them. They're uncorrelated degrees of freedom. Yeah?
So, you know, I was expecting, like, when you put U and down to an eigenstate, that you would just be summing the two energies into the same phase. If they each get their own little phase,
Yep.
it's just fine. Okay.
That's correct.
Okay.
Yep.
Okay. Well, I mean,
Yeah.
it is.
Yep. So the point here is that when we have a separable Hamiltonian, separable Hamiltonian implies no interaction, physical interaction between the degrees of freedom. Okay? Yeah.
This would be like when we do Cartesian components
Yep.
or multiple dimensions of a particle.
Yep, we're about to do that. Indeed. I just want to make one last comment about if this is not true, if the Hamiltonian is not separable, okay, if it didn't have this form, and I started in a product state, and I did the time evolution, then it's not going to stay in a product state. In that case, we call the unitary entangling. It's an entangling unitary because it creates entanglement. It creates correlation, quantum correlation. Yeah?
Would that be like two spin one half particles?
It would, I mean, it depends on the interaction between them, the physical interaction. So there's physics here. There's, you know, E and M and all that stuff. Quantum mechanics is not devoid of physics. All right. So, right. Okay, so now let's come to the kind of analysis here, looking at a specific case. Let's consider let's suppose I have a free particle. Okay. What's the Hamiltonian?
H equals p squared plus 2m.
P squared over 2n. Okay. If, say, this is in 3D, 3 degrees of freedom. Okay. Is this separable? Yeah, it's separable in px, py, and pz. We have to say separable with respect to what degrees of freedom. Okay? This is something that is almost always forgotten. That whether a state is separable or not depends on what tensor product structure we are imposing. Let's say, which degrees of freedom are we choosing to analyze the system with respect to? Yeah.
What if you used p sub r, p sub theta? And
That's the next step, so we'll come back to that. Yeah. He read my notes. But yeah, let's go get that in a moment. So this is this. Of course, what this really means is p sub x tensor the identity on y, tensor the identity on z, and this is the x tensor the identity on z, and this is blah 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 blah.
Well, why is the ordered form? I mean, I guess I don't understand these tensor products. I mean, I guess they're
You have to decide. If you're writing the state, right, I'm saying that there's, when I write this, tensor this, tensor this, tensor this, I have to talk about which Hilbert space I'm talking about. So this is Hilbert space A, or X, Hilbert space Y, Hilbert space Z. You just have to keep track of it.
And then that's different if I went Hilbert space Z, tensor Hilbert space A.
They're isomorphic Hilbert spaces, but in like the same way when you write down a column vector and you write down the components,
Okay.
you just have to know what you agreed on the order. I could order them any way I like, right?
Okay.
But once I write an order, I've got to keep saying that that's the order.
Okay.
It's just a bookkeeping. We would never do that, okay? But I'm just emphasizing that fact, just to say that this, in fact, is of the form I wrote. And this is separable. So there's a Hamiltonian that acts on the x degree of freedom, there's a Hamiltonian that acts on the y degree of freedom, and there's a Hamiltonian that acts on the z degree of freedom. Okay? And the joint eigenstates of the system are just the product of the eigenstates associated with those degrees of freedom. So I can write an energy eigenstate as px tensor py tensor pz. Okay. And the energy eigenvalue associated with these three eigenvalues is the sum of the eigenvalues associated with each degree of freedom, just as we said.
I mean, this is, I'm doing this in, excruciating formalism. You sort of know this. We've done this a million times. I'm just showing you how it all fits together.
Of course, that's just, the max p squared over 2n, where this is, and what is the eigenvector in position space? This is a momentum, I would say.
E to the I, P.
They're plane waves, right? The momentum eigenfunctions are plane waves, right? X, px is, with our usual delta normalization, e to the I x px over h bar. Right? And so the three-dimensional wave function associated with this xyz is x tensor y tensor z dx dy dz x dx y dy z dz. Notice, just as a, once you take the inner product, this is just normal multiplication by complex numbers. And this is e to the I over h bar pxx plus pyy plus pzz over 2 pi h bar to the 3/2 or e to the I over h bar p dot x. So the wave function is a product state, one for each degree of freedom, because the Hamiltonian is separable. All right. Now, let's get to, as Keith suggested, we have different ways of assigning degrees of freedom to the system. Okay. Right. I can talk about r, theta, and phi. Those are three degrees of freedom. And then I could write, I could try to say that the joint Hilbert space of the system is, instead of having a Hilbert space in x degree of freedom y, a, z, I could in principle do this. I could do that. Is my Hamiltonian for the free particles separable in that?
No.
Actually, it is. Yeah, it actually is. Because, of course, the momentum squared is equal to pr squared plus p. If you thought about it as a Laplacian, there's a derivatives that act on radial coordinates, phi coordinates, and theta coordinates. Right? Of course, this is just from classical mechanics, the angular momentum squared over r squared. Yeah.
But I mean, there's an r squared term in there though, so that doesn't mean it's dependent on r though, or no?
Sure. That is a good point here. It is dependent on r in that way. That is to say, I can write eigenfunctions which are, in this case, separable. So a free particle eigenstate, I would say there is some radial part that depends on r tensored into some eigenvector that depends on theta and phi. And that's a perfectly good, because I can separate that out. These kinds of eigenvectors are called partial waves, as opposed to the plane waves, the spherical waves.
Just one quick question.
Yeah.
So separation doesn't necessarily mean that it's not dependent. I mean, you can.
That's right.
Okay, okay.
Okay. Right. So, let's look at some example now with respect to the some potentials. So, because the system is always separable in the kinetic energy, for a particle moving in some number of spatial dimensions, or some number of particles moving in some number of spatial dimensions, whether or not the Hamiltonian is separable depends on the potential. Because we can always separate the kinetic energy. We can do it in cylindrical coordinates, we can do it in spherical coordinates, we can do it in Cartesian coordinates, but the question is about the potential. Okay? So if when we have a Hamiltonian, which is p squared over 2m plus the potential of the function position, then separability depends on the potential. Okay? All right. So, let's consider, for example, a particle in a box with hard walls, infinite barrier. Okay. So what I mean here, let's say a 2D box. So let's just talk about two spatial dimensions. Suppose my potential is of the form that it's 0 if x is inside of the square and it's infinity outside. Okay, so I have a box where the potential is 0 in here, and everywhere out here, it's infinitely high. Is this separable? Meaning, can I write this as a sum of a potential on the x-coordinate and a potential on the y-coordinate? Yes, I can. This is equal, where v of x is 0 if x is between 0 outside, and the same thing with right? So this is a separable potential. Okay. What if I had a finite potential well? Suppose that this were true. Suppose I had something like that. Okay. Where everywhere outside here, the height is v0. Is this separable? I mean, what if I wrote this? Is that the product? Is this plus this that potential? No, it's not, right? That's the one that would be, it would be v0, 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 2V0, 2V0, I think, right? I think that's right. Right, so that's not, this potential is not the one I wanted. The one where it's V0 everywhere is not separable. Okay, this is not separable. Now, let's go back to the infinite case. What are the eigenfunctions and eigenvalues of the Hamiltonian? Exactly, right? So, you know, for each one of these guys, so we have now my energy eigenfunctions. Are product eigenfunctions. They're specified by two quantum numbers. Where each one of these guys it depends where I put this guy. This is the way I would write it typically is I write in terms of even and odd. Well, this is cosine ni pi xi over L. Let me actually, it's important, I'm going to make this not a square. Let's say it's a rectangle. Okay, let's start with that case. So let's put that. Okay. And then I'd have this with the sine I meaning 1 or 2 meaning x or y for even parity and the odd parity. And the energy, let's go to the other board. The energy is just the sum of the energies associated with each of those. So the energy E and X, E and Y, H bar squared over 2m K X of NX squared plus KY of NY, where K, to meet the boundary conditions, for the I coordinate is equal to N I over L. Okay, that's how it meets the boundary conditions, as we know. So this energy is h bar squared over 2m pi squared. I'm going to factor out an Lx squared, nx squared plus ny squared, Lx over Ly squared. Okay? All right, so now one thing we see here is that whether or not there are degeneracies in the system, that is to say, if there are two different eigenfunctions that have the same eigenvalue depends on something about the ratio of these guys. So for example, if the ratio of Lx and Ly is rational, then we have degeneracies. Okay? So for example, suppose that Lx is twice Ly. Let's just suppose that were the case. I have that kind of rectangle, right? Then E1 1 here, right, is the same thing as what?
If nx is
Well, this is 2 squared, right? So if this is 1 and this is 2, that's the same thing if this is 1, right? Right? That's those two are the same. They're both equal to 5 times that mess, h bar squared over 2m, pi squared over ln squared. Huh?
Yeah, I don't know, is that, because it's 1 plus.
This is 1.
Uh-huh.
Did I get that backwards? Hold on a second. Well, whenever nx is equal to twice ny, right? And this is Did I, where am I messing that up? It's hard to do this is a case where I should look at my notes.
I think it would have to be 2 1/2.
No, I have to go the other way around then.
So the other one has to be bigger.
Yeah, in the way I've written it, I should it's this way. Ly is 2Lx. Hold on a second. I'm just getting.
So you just do 2 2 on the left side, and then it should be, I think, 2 1.
2 1. Which way we want to do this? Ly is sorry, got myself confused here. We want so let's say that Ly is 2Lx. It doesn't matter which way I do this, right? Then we have that the eigenvalue squares here are proportional to and so constant times this divided by 4. Right? So if nx equals 1 and ny equals 2, then the energy in this case is this constant times 2. Right? Now, is there another case where that's true?
5. So then this is equal to 5. And then n equals 2, and x equals 2, and y equals 1 equals 5. You buy it?
Doesn't that equal 8?
Yeah.
That's 2.
Why am I screwing this up so badly?
I think a higher,
Why am I screwing this up so badly?
larger
Algebra.
number would be
Nine.
better.
Let's look back. No one could see this either.
That's why I get too much. Where's Matt?
And now I can't get on my internet.
I'm gonna come back to it because I can't see the algebra right now, and obviously none of you can either. So I'm gonna just let this go for a moment and just say the following.
So I want to continue on, which is, we need some chalk.
There are degeneracies in this system. I'm just screwing it up somehow. But the point is here that these kinds of degeneracies are called accidental degeneracies. Although I can't seem to find the accident. Meaning that, you know, if they just happen to be that this were a rational number, there can be an alignment of these two things. Now, there's a very simple case where we can automatically see these degeneracies, and that is suppose that Lx equals Ly. Yeah,
I got one.
please.
2, 2, and 4, 1.
So nx equals 2, and ny equals 1.
Or ny equals 2 also.
Uh-huh.
And then the other one is 4 and 1.
4 and 1. Right. So in this case, we have, for in this case, squared plus 4. Yep, that works. Thank you. Yay! But that's an accident, and I couldn't find it.
Is that why they call it that?
Yeah. Because it's not in any way obvious. It just happens to be that it just happened to line up. But if this were true, well then it's obvious. If this were true, then this is true. Now, this is what we call, if this is the case, what this is a indication of is symmetry. The reason for this kind of degeneracy is the fact that if I have a square potential, then I have reflection symmetry. That is to say that v of xy is equal to v of yx. That is to say, if I flip these coordinates, the Hamiltonian is the same. So if I have a symmetry operator, let me just call it the reflection operator. And it's, I'll call it pi, which
sends x into y and y into x, and px into py, and py into px. Okay? Then the Hamiltonian is unchanged. Because the potential is reflection symmetric. So if I have a reflection symmetric potential, then the Hamiltonian is invariant under the reflection symmetry operation. Which means another way of saying that is the Hamiltonian commutes with reflection. Which means that the eigenfunction, there exist eigenfunctions, simultaneous eigenfunctions of the reflection operator and the Hamiltonian. So, if nx, ny is an eigenfunction, or I'll just put it this way. Is an eigenfunction of H, then pi acting on this is an eigenfunction with the same eigenvalue. See that? Let's review why that must be true.
So that's a tensor product, correct?
Yes, it's a tensor product. So as I said, often we just leave out the O times here because it's just too annoying to write it all the time. If I just write two cats next to one another, that's the tensor product.
Is it kind of like if you were like to put it into project it into X, you would just have the two functions multiplied? by
Correct,
each
that's
other?
exactly what it is.
Okay.
That's exactly what it is. That is to say, the joint eigenfunction of the system is equal to this eigenfunction times that eigenfunction. That's what it means. And so, what is what's that wave function?
Same thing.
See, this acts on this switches x and y. So that's u and x evaluated at y, and u and y evaluated at x. That's the reflected one. Now, I claim that these two functions are they're simultaneously eigenfunctions of the Hamiltonian with the same eigenvalue. They are degenerate. You see that because, so now I'm just going to simplify notation even further. I'll just specify them by their eigenvalues. This on the Hamiltonian acting on this with some energy. What is Hamiltonian acting on the reflected K.
Same energy, but the.
Right, it's exactly the same energy, because these commute. Because they commute, I can move the Hamiltonian to the other side. This then is the same energy eigenvalue. So, this is an important lesson. The point is that if we have a symmetry, in this case we had reflection symmetry. If there is a symmetry of the Hamiltonian, then there will be degeneracies. Symmetry and degeneracy are interrelated to one another. Because there is a symmetry operator that this commutes with, there are a set of different eigenvectors which share the same energy eigenvalue. Okay, that's sometimes, instead of called a accidental degeneracy, this kind of degeneracy is called an essential degeneracy. Okay. Let's do another example before our time is up here. Let's talk about a particle in a simple harmonic oscillator well in 2D. Okay? Yeah?
Do you mean that it has a 1/2 kx squared and a 1/2 ky squared for the potential? Or is it?
Yeah, exactly. So let me explain what I mean. Okay? So, for example, here's a simple, just a classical picture. Let's say I have two kinds of springs. I have a particle that's attached by springs, okay, to a wall. And there's a spring constant kappa x, and there's a spring constant kappa y. Okay, so I can pull it in either direction. And there's a resonance frequency associated with that spring constant and a resonance frequency associated with that spring constant. Okay? What is the Hamiltonian for this?
Dx squared plus 2y squared over 2m plus 1/2 m omega 1 or omega x squared plus 1/2 m omega y squared.
Right. Excellent. Okay? That's what it is. Okay? Is this a separable Hamiltonian in x and y? Sure is. What are the energy eigenvalues and eigenfunctions of the system?
H bar omega x.
So the energy, h bar omega,
H bar omega x times n plus 1/2
yeah,
plus h bar omega y times n y times plus 1/2.
yep. So there are two quantum numbers. Nx and Ny. Okay. Again, there can be accidental degeneracies in this system, but there's a special case that I just want to conclude with. The isotropic simple harmonic oscillator, say in 2D. Let's say that the two frequencies were the same. The springs were the same. So it doesn't matter how I pull it, it has a restoring force in that case, which is just proportional to the distance from the origin. It doesn't depend whether I'm pulling it along x or I'm pulling it on the y. It just says as long as if I pull it some distance r from the origin, it feels the same force. It's isotropic. Okay? In that case, we have something special. Well, first of all, the energy in that case, let's call that omega. Is that? Right? And we see this guy has degeneracy, right? So I have energies when, let's just make a little table here, nx and ny. So when nx is 0 and ny is 0, the energy is, I'll just call it 1, okay, in units of h bar omega. When this is 0, when this is equal to 2, etc., 3, blah, blah, blah. When this is 1 and that's 0, get 2, 3, blah, blah, blah. Now, when this is 1 and this is 1, then I have 3, 4, etc. When this is 1, this is 3. And I'm sorry, 4, 5, etc. So we see degeneracies here. There are many different combinations of nx and ny, which, in fact, we could write this. I mean, they're always integers, so the energy here is h bar omega times some n plus 1, where n can be 0, 1, 2, 3. But there's a degeneracy. Okay? And what is that degeneracy? N plus 1. Okay. So there's a degeneracy in this system, which means that there's really another quantum number m, but this guy is completely independent of that quantum number. It only depends on n, not m. What kind of degeneracy is this? Is this an essential degeneracy or an accidental degeneracy? It's essential. It's associated with what kind of symmetry?
E and x and y being the same as E and y and x, or the Hamiltonian leading with reflection.
It's true, it has reflection symmetry, but in fact this guy has even more symmetry than that. Let's look at the Hamiltonian again. P squared over 2m plus 1/2 m omega squared x squared plus y squared. This is my cylindrical coordinate rho. Okay. This is p rho squared plus p phi squared over 2m. Right? What kind of symmetry does this have? Remember, this is just the rate. This is just x squared plus y squared. So, what kind of symmetry does this have? It's rotational symmetry. The potential is independent. It's active. The potential here is independent of phi. It's azimutally symmetric. It's rotationally symmetric. This has rotation symmetry. It doesn't matter how much I pull it from the origin, at what angle, it sees the same force. Okay? So this has rotational symmetry. There's a rotation operator as a function of phi, and my Hamiltonian is invariant. respect to rotations around the z-axis. We see that classically because the potential is independent of phi, the conjugate momentum is conserved. Right? Remember that from Lagrangian mechanics. So there's a conserved quantity. What is that conserved quantity? It's this, which is, of course, angular momentum around the z-axis. The angular momentum around the z-axis is conserved because we have no torques, because the potential is independent of phi, which means that there is a symmetry. Conserved quantities and symmetries are one and the same. And quantum mechanics are also related to degeneracies. We will pick all that up and talk about angular momentum for many weeks to come.